It's all about the shape. In this unit, we will learn to draw Lewis structures, such as the ones we see here for the drug thalidomide, and use these to predict the three-dimensional shapes of molecules, as we see in the diagram below. Once we can predict the three-dimensional shapes, we can then use these to predict their physical and chemical properties. Now, it's important to remember that Lewis structures are only two-dimensional representations of molecules. However, molecules are actually three-dimensional. So here we can see two Lewis structures which at first glance appear to be different. However, by looking at the three-dimensional model of the molecules, we can see that those models are actually identical. And so therefore these Lewis structures are also identical, even though they may look different. The starting point for valence bond theory is the Lewis model, in which a covalent bond is formed by the sharing of electrons between two atoms in a molecule, as we see here. Now, although these electrons are shared, it's important to recognize that they may not always be shared equally. So, for example, oxygen attracts electrons more strongly than this hydrogen. To account for this fact, we introduce a new concept called electronegativity, represented by the Greek symbol chi. Electronegativity is defined as the power of an atom in a molecule to attract electrons to itself in a chemical bond. And so the shared electrons in a covalent bond will be pulled toward the more electronegative atom. This is important because electronegativity therefore tells us which atoms in a molecule the electrons will be pulled toward. An atom with low electronegativity is called electropositive, which is essentially the opposite of being electronegative. In this table, we see the trend in electronegativities. As we go up the periodic table and across from left to right, electronegativity increases. So fluorine, which is in the top right-hand corner of the periodic table, has the highest electronegativity of all the elements, whereas francium, which is located in the bottom left-hand corner, has the lowest electronegativity in the periodic table. Now, it's important to remember that electronegativities are actually unitless quantities. In addition, electronegativity is not a property of an atom alone, but rather it's the property of an atom in the context of a chemical bond. Now, in order to draw the correct Lewis structure, it's important to follow the outline for drawing Lewis structures. And this starts with the molecular formula. And we use the molecular formula to count the total number of valence electrons in the molecule. The next step is to draw the skeletal structure for the molecule. And atoms with the lowest electronegativity are placed in the middle of the molecule. Hydrogen atoms and more electronegative atoms are placed on the terminal ends of the molecule. Next step is to distribute our electrons, and in general we place 2 electrons in each chemical bond, and the remaining electrons we distribute as lone pairs. And we give each atom 8 electrons to form an octet. In the case of hydrogen, we give each hydrogen atom 2 electrons to form a duet. Okay. We add the lone pair electrons to the terminal atoms first, and then place any remaining electrons on the central atom. The next step is to check that each of the atoms has an octet, and then we form multiple bonds as needed by turning lone pair electrons into bonding pairs. Finally, we check the formal charges and follow the rules for formal charges to select the best Lewis structure. And this will lead us to the correct Lewis structure. The octet rule states that atoms will prefer to gain or lose electrons in order to attain 8 electrons in its outer orbitals, which corresponds to a complete or filled valence shell. In order to check whether an atom obeys the octet rule, we first count the number of electrons in it, where each lone pair represents 2 electrons and each covalent bond also represents 2 electrons. Now, it's important to remember that the octet rule only applies for carbon, nitrogen, oxygen, and fluorine. While the other elements in the periodic table can sometimes obey the octet rule, they don't necessarily have to.